So our first talk is going to be by Angie Wolfgang, Dr. Angie Wolfgang, who's a postdoc here at Penn State, and she is going to tell us about TESS, the Transiting Exoplanets Survey Satellite. Nailed it. All right, there you go.
Yeah. Nailed it. All right. Actually, Jacob, could we mirror displays real quick? Gracias. Okay. Right, so as Michael said earlier, just a few minutes ago, TESS, our next planet hunter, TESS stands for the Transiting Exoplanet Survey Satellite. It was scheduled to launch at 6:32 p.m. today. Unfortunately, they pushed the launch back, so we're not going to have that kind of extra excitement tonight, but tune in on Wednesday. It's still being broadcast on Wednesday. Hopefully this talk will excite you enough that you want to see the launch of this really exciting planet hunting satellite. Okay, so particularly, so we have... Hello? Okay, I accidentally turned it off. All right, so we have launched other planet hunters before TESS, all right? So part of what I'm going to be talking about today is what makes TESS so special. Particularly, what will TESS, as our next planet hunter, find? All right, so this is an artist's rendition right here of TESS. It's actually quite small. And it's looking for planets that transit their stars. Before I talk about that, though, just wanted to have a comment real quick about why do we even bother to search for extrasolar planets, search for these other worlds? Well, depending on who you ask, different people will have different responses. A physicist will say, I really want to understand planet formation. But I think all of us as just humans, we're intrinsically curious about whether or not we're alone in the universe. And this is one of the things that finding other planets really gets at, trying to answer this question. We also want to understand how unique Earth is, right? So related to that is how many planets are out there to begin with, of all different kinds of types, all that. And then also, one of the things that we have realized over the course of finding these extrasolar planets is that we're continually getting discoveries more and more that just completely blow all of our expectations out of the water. And so as we continue to explore new regimes of what these planets could be, at this point, after 25 years of finding exoplanets, most of us expect to be surprised. We expect to have brand new, unexpected discoveries. Okay, so this is great as a grand goal, and we have this really nice picture, suggestive picture here, of an extrasolar planet. Unfortunately, the reality is not so rosy as being able to see the surface of these stars. So this is an artist's rendition. This is not actually what we see. This is not the data that we take. So how can we actually find these planets? We find them indirectly by looking at their host stars and by continually monitoring the light that's coming from these host stars. So here we have a star. Again, from where we are, we cannot actually resolve the surface for the vast majority of stars we look at. And the way that we're monitoring the star is by taking data about its light as a function of time. Okay, so not all stars have planets. Let's say that this star does have a planet orbiting it. All right, so we have the planet here along its orbit. As this planet orbits in this configuration, we're over here and we're staring at the star like this. Then we're monitoring the light as a function of time. Okay, and the way that this planetary orbit is oriented, we do not see any change in the light from the star due to the planet. The star is moving itself, so there will be some variations here, just to the star, but we don't see anything due to the planet yet. However, what if we take this orbit, where the planet's orbiting in this direction, And all of a sudden, we think of a new system where the planet is orbiting like this. So it's orbiting in and out of the plane of the monitor. Then, what we have is this. So we have the planet passing from behind the sun along its orbit, and then it's going to pass in front of the star, and it will all of a sudden dip, block out some of the star's light. And so we are continually monitoring a whole bunch of stars. Then those that just happen to have the orbit in this perfect configuration so that the planet is just at the right angle with respect to our vantage point, then it will block out some of the light from that star. And we can see that with this kind of dip. And we call this a light curve here. Okay, so we can figure out a couple really interesting things about the planets this way. So the time between consecutive dips, that gives us the orbital period of the planet. And through Kepler's law, that gives us the distance between the planet and the star. So we can tell how far the planet is from the star. What about the depth of the dip? All right, well, let's consider two possible scenarios here. We have a large planet and a small planet. And before it passes by, which one do you think is going to be deeper? The bigger one. Yeah, exactly. It's an area effect. It's the amount of light blocked out from the star based on the area. Right, so from the depth of the dip, we can get a sense for the planet's size. All right, so the primary things that we get out of missions like TESS or Kepler before it is the period of the planet's orbit, and then also the size of the planet. Okay, so I just mentioned Kepler. So Kepler was one of our first planet hunters in terms of space-based missions. And it did a lot of groundwork for what we understand now about extrasolar planets. So Kepler was a statistical mission. What that means is that its primary goal was to figure out how many planets of each size and each orbital period exists out there. Okay? So in order to do that, I just stared at one patch of sky and just did this continual monitoring over the course of 4 whole years. And from that, we were able to figure out the relative frequency, the existence of Earths. So here, Earths are defined to be about 80% the size of Earth to about 125% the size of Earth. Super Earths up to 2 times the size of Earth. Mini Neptunes. So you can tell that these are names inspired by our own solar system. Mini Neptunes between about 2 to 4 times the size of Earth. It turns out Neptune, so that's what is up here, that picture. Neptune is 4 times the size of Earth. And then larger Neptunes and then gas giants like Jupiter and Saturn. And what we found from Kepler is that these are the relative frequencies that these sized planets exist in our galaxy. All right, so particularly, if you add all of this up, and this is a slightly outdated result, there's been new ones recently, there's about 1 planet per star. This is what Kepler has told us. Also, planets smaller than Neptune, so these 3 bars, end up being about 20 times more common than larger planets like gas giants. All right, so we're finding that Jupiter and Saturn are actually not super common in other planetary systems. In fact, what is much more common are these planets between the size of Earth and the size of Neptune. And it just so happens that in our own solar system, there are no planets in this size range. We have no analogs for the vast majority of planets that Kepler has found. This is an example of one of those really unexpected, exciting discoveries that are really par for the course in this field. Okay, so I just talked a little bit about radius, right? But remember, period is another thing that we can understand about planets based on transit surveys. So if we look at both of them and count the number of planets in both radius and period, Then we get a diagram that looks a little bit like this. Okay, so there are a lot of numbers up here. Ignore the numbers, pay attention to the color. Okay, so the more purple, the less frequent that kind of planet. The more red, the more frequent that kind of planet. Okay, so here we have radius on the y-axis. This is in terms of Earth's radius. And then orbital period in terms of days on the y-axis, or x-axis. Okay. To give you a little bit of context for another aspect in which these planets are really surprising, here we have Mercury's orbit. Mercury orbits the sun every 88 days. In our own solar system, Mercury is the closest planet to our star, to the sun. We have all of these planets that are way closer to their stars than anything in our own solar system. This is another example of something that was really unexpected. And so, especially now that we know that there are all of these planets super close, this really inspires us to try to understand what these planets are like. In particular, this is an artist's rendition of a hot Jupiter. So Jupiter, meaning that it's about the size of Jupiter, size and mass of Jupiter. Hot, that is a comment about its orbit. So it orbits its star every 3 days. That is very, very close to that star. And in fact, it's so close that this hot Jupiter is evaporating. The light from its star is actually driving off material from the surface of the planet. And we have found several examples now where we've actually detected this material being thrown off of the planet. Okay. So I commented about how there are all kinds of planets interior to Mercury's orbit for other solar systems, but there are also plenty of planets that are just slightly farther away. And in fact, the analysis that goes into this shows that the planets that are even more slightly farther away should be more frequent in nature than the ones that are close, that we easily found just blew us away. Okay, so I just talked a little bit about what Kepler has told us about extrasolar planets. All right, so that was its job, to try to map out and give us a sense for what kinds of planets are out there. So what will TESS do? Okay, well, so TESS is going to find similar numbers of planets at different sizes. So Earth, super sub-Neptunes, and then giants. It will mostly find these sub-Neptunes and super-Earths that we talked about, but a few dozen Earth-sized planets, about 50, okay? And so in terms of orbital period, how far away they're going to be, to answer this question, you need to ask, how long will TESS search? Okay, so I have a video here, and it will explain to you a little bit about the observing strategy of TESS, and particularly how it's different than what Kepler did. So Kepler just stared at one patch of sky for 4 whole years in order to do these counting, exoplanet counting. This is what TESS is going to do.
During its 2-year survey, TESS will watch a wide variety of stars, looking for signs of planets ranging from Earth size to larger than Jupiter. Each of TESS's cameras has a 16.8 megapixel sensor covering a square 24 degrees wide, large enough to contain an entire constellation. TESS has 4 of these cameras arranged to view a long strip of the sky called an observation sector. TESS will watch each observation sector for about 27 days before rotating to the next. It will cover the southern sky in its first year, and then begin scanning the north. TESS will study 85% of the sky, an area 350 times greater than what NASA's Kepler mission first observed, making TESS the first exoplanet mission to survey nearly the entire sky.
All right, so that is half of the reason why TESS is so exciting, is because it is really going to be an all-sky survey and really looking at all the stars that are brightest in our neighborhood. As far as the orbital period of these planets that TESS is going to find, because of the way that it maps out and observes the whole sky, it's actually only going to mostly find close-in planets. Okay, so here we have this map of how much time TESS spends in any given region of the sky. And as you can see, most of this is light blue, which means that it's only observed for one sector, one 27-day segment. But at the very top, consecutive sectors overlap. All right? And this is really exciting because this is right where the James Webb Space Telescope is going to focus a lot of its observation time, especially for exoplanets. So this is the region where JWST is going to focus. As you notice, this is also the region that has the most coverage for TESS. All right? So why is James Webb so interesting and so valuable for exoplanet research? It is with James Webb that we can really probe exoplanet atmospheres. We can get down to smaller planets and observe molecules that are not quite as abundant in the atmospheres as we currently have. Currently, we have several dozen planets that we have observed their atmospheres for. James Webb is going to enable us to do much more than that. Okay, so I talked a little bit about the all-sky nature of TESS. But the other half of it that is so exciting is that TESS is going to be targeting finding these exoplanets around the bright stars. Okay, so what I'm showing here is the brightness of the star. Okay, so anything that falls above here, if you go out at night when it's clear out, you can actually see with your naked eye. Anything just slightly dimmer than that, you would need a binocular. Anything dimmer than that, you need a telescope. Okay, so that's the y-axis. The x-axis here is the planet radius, the radius of a planet that could be detected around that star. Okay, so here again we have the comparison between Kepler in the blue. All of its target stars were actually pretty faint. And that just turns out that happens when you just pick one part of the sky to stare at. Most of the stars in that one patch of sky are going to be pretty faint. But we needed to do that in order to get these counting statistics. Now that we know that exoplanets are abundant and they're out there, one planet per star, I mean, that's amazing. Now we can go target the brighter stars. And the reason why we want brighter stars is because those are the ones that are easier to observe. It's easier to go back to that star and take spectra of it. Try to do mass measurement, observe their atmospheres, these kind of things. These kind of things that really characterize what the planet is like. That's possible around the brighter stars. Also, just a note about the all-sky nature of this. So these are some of the projected detections across the entire sky that TESS will give. All right, so you can really see that exoplanets are everywhere in the galaxy over the entire sky. Okay, so all of this gets us one step closer to answering, are we alone? All right, so this is a really grand goal far in the future, but a lot of the things that exoplanet astronomers do inform, are trying to get at, are we actually alone? All right, so before I conclude and take questions, this had said after launch at 6:32 p.m. Oh, that would have been perfect. But after launch on Wednesday, just wanted to give you some context for what TESS as a satellite is going to be doing and how it gets set up to do these kind of observations. So I have another video. It just takes a couple minutes.
TESS will fly in a special, highly elliptical orbit that maximizes the amount of sky the spacecraft can image. Once TESS has launched, it will expand its orbit until it can get a gravitational assist from the moon. This slingshot will move it into a stable orbit that is tipped at about 40 degrees from the moon's orbital plane. TESS orbits Earth in exactly half the time it takes the moon to orbit once. This feature helps stabilize the spacecraft's orbit against tugs from the moon's gravity. TESS will spend most of its 13.7-day orbit observing the sky. As it approaches Earth, TESS will rotate and transmit all its accumulated data to scientists on the ground. Over 2 years, this will allow TESS to study nearly the entire sky and potentially find thousands of new exoplanets.
Great, thank you. I'll take questions.
Yeah, there's a question that always shows up when we talk about transit discoveries like that. They're always drawn as though the planet is passing in front of the star right across the equator, right, which you know is not true. One extreme is it's 90 degrees to that, and you don't see it at all. But the relative size of the planet and the star and the orbital inclination have got to both affect the light curve. So how do you tell an inclined orbit with a, let's say, a large planet versus a small planet that's equatorial?
Okay, so the question is, so in these kind of animations that demonstrate the transit technique, almost all the time the planet is shown as crossing the equator. But that is not how nature works. Nature has more variation in that. So how can you tell the difference between a planet size and its orbital inclination based on the light curve? Okay, so the inclination is best probed by the shape of the transit. So in the animation that I showed, it was very, very boxy and U-shaped. You can imagine that if that transit chord is closer to the limit of the star, first of all, that box is going to be shorter. It's going to be shorter in duration. But it turns out that stars are not uniform brightness over their entire surface. They are dimmer, usually, at their edges. Yeah, so this is what's called limb darkening. And so how this manifests in the shape of the transit is that the planet spends more time crossing the limb of the star where it's dimmer. And so the ingress is a little bit shallower and the egress is also a little bit shallower. So there is a little bit of dependence on the depth of the transit, but the depth of the transit correlates more strongly with the relative size of the planet and the star rather than the inclination.
So Kepler would stare at one spot for like 3 years to catch multiple transits to confirm things. So how do you know that staring at a small patch of sky that represents like 0.28% and you're only seeing the planets that are in the right inclination plane? A, how do you know that's a correct representative sample? And B, if TESS isn't doing that, when it swings around and sees transits, how do you know if that's, I mean, you can probably tell by the light curve whether it's the same planet or not, but how do you tell how many planets, or can it just not do that like Kepler can?
Okay, all right, so two-part question. Okay, first part, Kepler stared at one patch of sky. How can we tell that that one patch is representative? The planetary systems in that one patch are representative. Okay, so I'm going to address that one first. So there is the orbits of planets are isotropic. The inclination of them are isotropically distributed. So they're completely random whether they are face on like this or whether they're edge on like this. So if you observe a large enough sample of stars, so Kepler observed 200,000 stars, this is actually part of the reason why it took a little bit of time for Kepler to be launched, because people had to demonstrate that, yes, they would actually be able to find planets given a sample of 200,000 stars, because when Kepler launched, we didn't know how many planets were out there. But it turns out planets are abundant, so awesome. So there is a little bit of a nuance there in that the planet properties could vary at different positions in the galaxy. Right now, we don't really have evidence that there's any variation based on where in the galaxy a star is located. And we can start to probe that because when Kepler's reaction wheels failed, then they pointed to a completely different place in the galaxy and sampled a much larger area of the galaxy. And it turns out that it's a little bit harder to do this counting statistics with the K2, the repurposed Kepler mission, but when you do a first stab of it, it does not look like the statistics are any different depending on where you're pointed in the galaxy. Okay, the second part of this question is TESS, right? So TESS is not going to be staring at the same patch of sky for 4 whole years. So how can you tell how many planets there are? Right, okay, so yes, we might miss planets. Especially ones that are farther out, right? So what TESS is requiring is that we see at least 2 transits of a planet in order to kind of consider that detected officially by TESS. But there's going to be a whole bunch of planets that are at longer orbital periods so that they only transit once while TESS is staring at the star. And so that's actually exciting for everyone in the community because we have the opportunity to go back to that star, say, we found this really interesting dip, but we want to make sure that that is due to another planet in the system. By the way, multiple planet systems are amazingly awesome. They have a ton of information. That's another unexpected thing that I didn't even talk about that Kepler totally blew out of the water, is that multiple planet systems abound. So this basically presents a really exciting opportunity for everyone in the community to get all hands on board and follow up these test targets. And again, they're bright, so we can actually do that.
I hear that amateur astronomers are now detecting exoplanets from their backyard, and they're doing it by taking an $800 Canon camera, and they take 200 or 300 photographs of the field. Then they stack them, run it through a computer analysis program, and they can detect the transit. Is that actually happening? And is anybody in this room doing that?
So I'll open it up to you. So the question is, indeed, yes, amateur astronomers are detecting extrasolar planets from their backyard. I have several colleagues at primarily undergraduate institutions who have a small telescope at their disposal, and this is their undergrad project for their astro majors, is to find. Usually only the largest planets are really possible from the ground. But it is possible to find them. And yes, so you can do it. It's really exciting that, just in the last couple decades we found them, and all of a sudden the technology is good enough that we can do this from the ground with relatively cheaply.
What's been done from Davy Lab?
Yes, yeah. On top of Davy Lab, there's several telescopes. Some much bigger than what other amateurs are using to detect extrasolar planets. Carol, did you have a question?
I did have a question. So what is TESS's nominal, 2-part question, what is the nominal mission time for TESS?
Okay, the nominal mission time is 2 years.
Okay, so my question is, are there any expendables and what are the prospects for an extended TESS?
Okay, so the question is, what are the prospects for TESS being able to observe longer than 2 years? So there are not very many expendables. So in talking to the PI of the mission, he has indicated that TESS could potentially take data for 10 or more years. Yeah. So we like to build stuff so that once it is up there, it gives us a lot of bang for our buck. So we could potentially be going back to this question of how do we know if we only observe a star for 27 days, how can we tell whether or not there are other planets there? Well, if the test lasts more than 2 years, we can totally go back to those same fields and look at it again and try to follow up these single transit systems.
Good question. A really curious, simple question. Your model seemed to indicate a gray band in the middle. Is there an area that TESS will not be able to sample?
So in the nominal mission, there is a region around the ecliptic that is not currently in the plans to be observed. But there's a grad student at MIT who's done simulations about extended missions for TESS and what the various options are. And so one of the options is to look at the ecliptic again. So a note about the ecliptic, that's where the repurposed Kepler mission pointed. And it was constrained to the ecliptic because that's the only way that we could get it to point well enough with 2 reaction wheels dead. So we already do have some data there, and TESS is going to be complementing that, so that's really exciting. Okay, so the ecliptic plane is basically the plane in space that is kind of mapped out by the Earth and the Sun, our orbit around the Sun.
So when are we going to find aliens?
Okay, so when I'm sitting next to someone chatty on a plane, and we get to talking about what I do, this question inevitably comes up, and my response is always, okay, so I love this question, but I have to take off my scientist cap, because currently we don't have any evidence that there is life out there. Having taken off my scientist cap, I can say from a personal perspective, I think it would be very arrogant of us to think that we were the only ones out there. That's my take on it. So I think that there's a good chance that there's life out there. The tricky thing is going to be finding incontrovertible evidence that that is the case.
Thank you, Angie.